I finally built a dual GPU setup. These are two AMD Radeon 9700 AI Pro. Each comes with 32 gigabytes of VRAM, giving the system a total memory of 64 gigabytes. These are consumer-grade cards based on the new RDNA 4 architecture, and they are positioned for local AI workloads. At the time of this recording, these sell for around £1,200 in the UK. However, with the current memory supply constraints, prices will go up. But at the time of this video, you can still find some of these cards for relatively good prices. In this video, I want to share two things. First, I will walk you through what I learned building my first dual GPU setup. I am a software guy, and the last time I put together a desktop PC was back in the early 2000s. So last weekend, I enlisted the help of a good friend of mine, Emilian, who helped me put together this build. I'll walk you through all of these specific considerations for a dual GPU setup, like this one, such as airflow, number of PCIe lanes, and power demand. You need to take all of these into account if you want to build a similar system. Second, I will show you how to configure llama-cpp to run LLMs and get good performance out of this setup. Now, I know many of you want to see VLLM instead of llama-cpp, and I am working on it, but the reality is that support for AMD consumer GPUs is still not very mature, and for a single-user local server, llama-cpp is currently the most versatile and convenient starting point. But there are advantages with VLLM, especially for dual GPU setups like this one, because you can use tensor parallelism. So we'll look at that in the next video. Before we move on, I know that most of you are here because you are considering buying this GPU and want to know if it's any good and how it compares to other options on the market. The problem is that fair comparisons are genuinely hard here, because AMD is targeting a very specific gap. Right now, there is basically nothing else in the $1,300 price range that offers 32 gigabytes of VRAM on a modern architecture with solid AI support. That combination is what makes this card extremely compelling. The only other consumer GPU with 32 gigabytes of VRAM is Nvidia's RTX 5090, but that sits in a completely different price bracket. It costs close to twice as much at the current prices, and yes, it is significantly faster for Gen AI workloads. For one thing, it has much higher memory bandwidth than the R9700. But once you start thinking about real setups with 64 to 128 gigabytes of VRAM, meaning 2 or 4 GPUs, the price difference becomes considerable very quickly. The other option that is close is the RTX 4090, but it only comes with 24 gigabytes of VRAM. It's still more expensive than the R9700 and quite hard to find at the moment. And again, VRAM is really important to run decent models. I would not go for a 24 gigabyte card heading into 2026. Architecture also matters. You can find older cards with similar memory, but they lack support for data types that are common now in Gen AI workloads. This means that some operations will be slower or in some cases not supported at all. RDNA 4 supports a wide range of formats beyond FP32 and FP16, including low precision formats like FP8. For example, Red Hat releases many models for VLLM in FP8 format that will run very well with 32 or 64 gigabytes of RAM, but you can only use those models if your GPU architecture supports that low precision number format. In a nutshell, the R9 700 is a calculated compromise between peak performance, memory capacity, and price. You don't get the RTX 5090 performance, but you still get a large amount of VRAM at the best price point available right now, which is really important, especially if you plan to use 2 or more of these GPUs. Okay, first let's go over the components we used for this workstation. Of course, we have the two GPUs, the AMD Radeon AI PRO 9700 cards, each has 32 gigabytes of DDR6 memory. The CPU is the AMD Ryzen 9 9900X3D. For the motherboard, we have the ASRock X870E Tai-Chi, and we paired that with 64 gigabytes of Crucial Pro DDR5 RAM running at 7000 MHz. For the storage, we installed a 2 TB Gen 5 NVMe SSD. Powering the system is the Corsair HX1200i power supply. And everything is housed inside the Fractal Design torrent case. As I said earlier, I am a software engineer, not a hardware builder. I haven't built a PC in over 20 years, so I enlisted the help of my good friend Emilian, who has significantly more experience than I do building computers. And I learned that there are 3 specific things you have to get right for a build like this. The first is airflow. Now, when you put 2 of these cards in a motherboard, they tend to sit very close together and they generate a lot of heat. A friend of mine described it as turning on an oven inside a shoebox. If you don't move that heat immediately, the temperatures are going to get critical pretty soon under heavy AI workloads. And this is why I chose the Fractal Design torrent case. It has 2 large front fans that push a wall of air directly between the PCIe slots. And it's not about the aesthetics, it's literally forcing air into that gap to prevent the top GPU from throttling. The second consideration is the motherboard and CPU combination. For me, this was the biggest learning curve. To understand why the motherboard and CPU matter a lot, you need to have an understanding of how the CPUs connect to the system. They connect using PCIe lanes. You can think of these as the physical pipes that carry data between the cards and the CPU. Now, a standard full-size graphics card slot is technically called an X16 slot. The 16 literally stands for the number of lanes that the card is physically wired to use. Now, ideally, you want to connect all 16 lanes to the CPU. But most consumer CPUs simply cannot support that many lanes. For example, the Ryzen 9900 we have here is only using 24 lanes for the entire system. And you can't even use all those 24 lanes for the graphic card because the system reserves some of them for your NVMe drives and to talk to the motherboard's chipset. So, once you subtract those reserved lanes, you are left with exactly 16 lanes available for the graphics. And since we have 2 cards and they each physically want 16 lanes, we would need 32 lanes in total, and the CPU simply doesn't have them. So to get enough lanes to run 2 cards at the full 16 lanes, you would need a Threadripper CPU, for example, which costs much more money. And this is where the ASRock X870E Taichi comes in. It takes those 16 available lanes and splits them evenly, giving 8 to the top card and 8 to the bottom card. Now, this is not that bad as it sounds because the R9 700 card support PCIe Gen 5. A Gen 5 lane is twice as fast as the previous generation. So even though we are only using 8 lanes per card, the speed is roughly 32 gigabytes per second. And this is equivalent to a full X16 connection on the older Gen 4 standard. So we get the connectivity without the bottleneck. The third consideration is power supply. Here we used the Corsair HX 1200i, which supplies, as the name says, 1200 watts. We chose this based on a simple calculation. Each GPU is rated 300 watts, so that is 600 watts just for the pair. And you add in 120 watts for the CPU and 100 for the rest of the system, and you are already looking at a sustained load just below 900 watts. So 1000 watts PSU would have just done, but we went 1200 watts to give us a little bit more headroom. And I understand this is actually good practice because if you run too close to the limit, any power spikes could trip the power supply protection and shut your system down. So in the second part of this video, we are going to get LLMs up and running on this server using llama-cpp. Because I haven't had time to script this second part of the video, here I have a table of contents just to remind myself of the points I want to talk about and to minimize the amount of rambling that otherwise I would engage in. So we are going to start from the operating system. I installed Fedora 43. This is the latest version of Fedora, very recent, and I find it works really well for anything Gen AI. And after I installed it, you can see here actually the kernel that I am running. It's very recent. After I installed it, I'm running these in multi-user mode, but without a UI, so that I can SSH into it and use it as a proper server. I think everything I'm showing you would work fine, even if you were just using it as in its graphical form. Now, the one thing that I do at this point, I install ROCm from the official Fedora repositories. So you can do sudo dnf install ROCm. And you do not need ROCm to be installed on Fedora because we are going to be using my toolboxes, which have different versions of ROCm in them, but having ROCm installed actually does help because it allows you to access tools from the operating system, such as ROCm info, which are going to give you information about your GPUs. And also another very useful tool is AMD GPU Top, which allows you to access live stats about your GPU usage and temperatures, power draw, and all sorts of things. Okay, so ROCm is finished installing, so we can go in here now. And again, the main reason why I installed ROCm is that we can get the ROCm CLI tools, for example, ROCm SMI, which is similar to Nvidia SMI, and then ROCm info, which is going to give us detailed information about all of the GPUs we've got. So for example, we can go from the top and you can see here that we have actually 3 GPUs. We have the one integrated in the processor, and we're not going to use this one for any Gen AI, but ROCm sees that. And what we care about is these ones over here. So the first Radeon AI Pro 9700, and its architecture name is GFX 1201. So this is one of them, and you can see all of the details. For example, the number of compute units 64, and obviously we can see the second one over here. So this also confirms that everything was installed properly. The other thing that I always install on my operating system is AMD GPU Top, and this is a tool that allows you to look at the live statistics about the GPU utilization. It's very useful, and on Fedora you can just do cargo install AMD GPU Top and it's going to install it. I've got it already installed, so if I go AMD GPU Top, that's what it looks like. I can see one of the GPUs. Obviously we're not using it now, so there is nothing showing, and I can press ESC and enter, and I see the list of all of the other GPUs. So I can move down, and this is the second one. And once we're running models, we're going to see these light up as a Christmas tree. Okay, now what we're going to see is how do we get the llama-cpp builds on this particular host. You can go out and build your own version of llama-cpp, but to make things easy, and you know, if you've seen my videos on Strix Halo, what I did here, I have created a repository where I maintain and build different Docker containers that map to different backends and different configuration backends for llama-cpp to work on AMD GPUs. Now, I will point you to my original video on the other AMD GPU to get more of an idea, but in a nutshell, there are two main backends that can be used by llama-cpp on AMD GPUs. You have Vulkan and ROCm. And within Vulkan, as you can see here, you have the RADV, which is the open source driver, which is typically bundled, or you can easily install with your packet manager. And then you have AMD VLK, which is the proprietary version of that Vulkan backend, but this has been discontinued by AMD. They still offer it. You can still download the latest version, and the reason why I include this is that at the moment, for some models, this still works very well, or is even the best alternative that we have. Now, on the other side, you have ROCm. ROCm stands for well, I mean, I don't know where the acronym is here, but it should stand for Open Compute, Radeon Open Compute Platform, or something like that. And this is the main ways, this is the equivalent of CUDA, and it is the main way that software can use to access some of the GPU operations. Now, what's complex at the moment is that we have different versions of these backend. We have the 6 series, 6.4.4, which is quite recent and has got a lot of support for all of these GPUs, and I find it works really well in most cases. Then you have versions of these that I have compiled with something called ROCwMMA. This is something that in certain cases will make inference on models faster. And then we have the ROCm 7, which is newer and bleeding edge. And here I have the nightly builds. So these come directly from something called the ROC, which is what AMD uses on a daily basis to kind of build these development branches. So that's very bleeding edge, and sometimes it works really well, sometimes it doesn't. And then we have ROCm 7.1.1. This is really the one you should be using. And you also have like 7.9, but typically you don't need to use this. Now, the only reason I've put all of this together, you shouldn't worry too much about the individual details, but what I do, I run benchmarks. So I take different models with different architectures and sizes, and then I take all of these backends here, you can see here, and I benchmark them with llama-cpp so that you can see right now, given a certain model, which is going to be faster for your use case. So here you see the benchmark for what's called prompt processing. So given a prompt of a certain length, how long will it take to process on that particular backend with this GPU? And then you have the second table, which is token generation. So how long does it take to generate tokens? And you have here different context sizes. There is the default context, which I think is 0. And then there is a context of 16,000 tokens and a context of 32,000 tokens. And obviously, the longer the context, the slower it's going to be. And this is particularly important if, for example, you want to do a coding agent or use this for coding, because it's likely that you are going to pass a large set of files with your source code, and you need this to process it before it starts generating tokens. Now, the way to use this is very simple. Let's say I am again interested in coding and I want to use Qwen3 Coda. I can come here and maybe I want to use it in this quantization. I can sort it. And this is going to tell me which of those backends are going to perform better for prompt processing, which is really important. And here I have a choice. As you can see, many of them perform very similarly, 2,900 tokens per second or close to that. But then if you go to the right side, for example, I would not choose Vulkan RAD on this architecture and quantization, because it's basically less than half the speed. So this is why this is important, but it's not going to be the same for all models. For example, if you go on this one over here, this is Qwen3 Coda with a different quantization or not quantized. In this particular case, Vulkan RAD, which didn't perform very well, it's going to perform much better. Something else to keep in mind here is that sometimes you see dual GPU. This one was running on a single GPU because it didn't need two of them. This one is larger because it's brain float 16 rather than this quantization, so this needed two GPUs. But the reason why I'm showing you this is because there is not one backend that's gonna outperform the others on all model architectures and configurations. So hopefully this benchmark allows you to choose what you want to use for your case. Now, once you know that, you can get one of these toolboxes very easily. So you can create a Vulkan toolbox like this. In this case, I am creating the Vulkan RAD toolbox. And what's important is these devices. So this is what's going to make the GPUs available to the toolbox. Remember, a toolbox is essentially a container which is going to be run, and you're going to get shell access to it. So it's going to feel like you're not in a container, but you are on your main system, and your home directory, it's going to be mapped there. It's probably one of the easiest, most convenient ways to use my toolboxes. Now, if you want any of the ROCm toolboxes, like for example 7.1, you are going to need a different set of devices to be passed. In particular, you are going to need this additional device, because ROCm requires that in order to function. Now, let's say we want to take one of the ROCm ones. We just take the command, we go here, and you run this, and it's going to go out on Docker Hub, download it, and make it available on your system. Now, in my case, obviously, I had already installed it, so I can run toolbox list, and you can see I have actually all of them. But in your case, you're probably going to have only one or two of these. Now, if you are on Ubuntu or OpenSUSE instead of Fedora, chances are the version of Toolbox that ships with these distributions is a little bit different, and it doesn't work very well, especially with passing all of these devices. So some users have reported that they find if they install DistroBox on Ubuntu instead of Toolbox, and so they use DistroBox by typing DistroBox instead of Toolbox and then the same syntax, this just works and the toolboxes work fine. So essentially you can use Ubuntu provided you use DistroBox. Now, once we've got a toolbox downloaded and created, we can enter it. So we can do toolbox enter, and let's say we're going to get the ROCm 7.1.1. This is one of the, again, more recent stable ones, and this drops us into a shell. Again, don't forget that here you can see your home directory from inside the toolbox, and this is going to make it actually quite easy when you download models to access them. For example, I've got all of my models in my home directory in the models folder. Now, once you are in here, you can type llama-cli list devices, and this is going to show you all of the GPUs that llama-cpp can currently see with the backend we have installed. And you can see the two Radeon Pro, so this confirms we've got them installed correctly, and you will again also see the integrated iGPU. We are obviously not going to use the integrated GPU in the processor. We only want to use the fast, efficient discrete GPUs. And actually there is an environment variable called heap visible devices that you can set, for example, to 0. And if you do that and you rerun llama-cli, I think I made a typo, right? Visible devices. You can see that now the only GPU that llama-cpp can use is the first one. And this can be useful sometimes when you want to just isolate one of the GPUs. And obviously, if I do 0 and 1, this now can see both of my GPUs. So we've got the toolbox installed. Now, one thing I want to tell you actually before we go on that I forgot to tell you is that these are running very recent versions of llama-cpp, because my repository here has got an action where twice a day it checks the llama-cpp repository and rebuilds all of the toolboxes if there is any change. And there is a lot of activity on llama-cpp. Specifically, there has been a lot of activity, such as you can see here, for example, very recently, just I think a few days ago, this PR to support RDNA 4, or to improve support for RDNA 4. And this was merged just a few weeks ago, or even just last week, into the main branch of llama-cpp. Now, when I first built the server, this wasn't merged in, and I had very not great performance, and now that this has been merged in, performance has improved. And by speaking to the people that are actually working on llama-cpp, there is now a lot of work going on into improving support for AMD GPUs and ROCm. So in the next few months, there is a lot of headroom so that all of these benchmark that I showed you, I cannot guarantee it, but it is very likely that there is a lot of performance that can be achieved in llama-cpp by better using these. And again, as you can see from the evidence here, from this PR and a lot of other PRs that these people have been working on, they are now targeting specifically these GPUs on llama-cpp. So I wanted to tell you that so you keep in mind that all the performance that we discuss, it's likely, very, very likely to improve. But anyway, you always want to refresh my toolboxes so you get the latest possible version. Now, you've got the toolboxes and you want to run a model. To get a model, you need to download it, and let me show you how to do that. So I have here a command that you can run, hf download, and then you can specify a model to download, and you can take all your models from Hugging Face. So let's say I was interested in one of the new Ministral models. So what I am going to do, I'm going to set the GGUF filter. GGUF is the format used by llama-cpp. And then what I recommend is typically to find any version of that model made by Unsloth. I've already spoken about a slot in my other videos, but you can see here the ease of use of llama-cpp because you have all the different quantizations of the model. So most models today come in BrainFloat 16. So you can see the amount of space that it's going to require. And then you can see the other quantizations. So typically, for example, these are 8-bit quantizations. This is a normal 8-bit quantization, and this is an 8-bit quantization with XL. These are dynamic quants where not all the weights are quantized to 8 bits. Some things are left at their full precision because they have more impact. So typically Q8K actually performs very closely to the actual full model. And I will say from experience that typically Q8K also performs very well, approximates that model very well. So let's say I want to get that quantization. One easy way to do that is to find that file in here. So the dynamic quants, again, I've got these UD, I think it stands for Unsloth dynamic quants. And let's say, again, I want this one over here, Q4KXL. So this is the repository name. So I'm going to copy this and I'm going to do hf download. If I can type it. So I put the repository name and then the name of the file. So the directory and the name of the file. And then for me, I'm going to say local directory, and I'm going to point it to a directory. In my case, I have the models folder in my home directory. Or you can put the current directory, you press enter, and this is going to go and download the model. I'm going to kill it because actually I've already downloaded that model in here. You can actually see, or maybe actually I haven't, so I could have downloaded that model. Now, once we have the model weights, a lot of these have just one file, but some of them, for example, if we look at GPT OSS, I look for my Unsloth version of the model. But what I wanted to show you is that some of these, because of the size, they are split into multiple GGUF files. So you have to, if you use the method I showed you, hf download, you have to first download this, and then you have to rerun it and download the second part. So don't forget to do that. So you've now downloaded your models. As I said, I've got my models in my home directory. And now if you want to run any of these with llama-cpp, first you can do llama-CLI, which is a command line tool, and you are going to say ngl99. This is how many layers you want to offload, and 99 is a very high number. You're basically saying any layer is going to be offloaded to the GPU, and then we can say the model we want. In this case, for example, I'm going to take this Qwen coder model. But before I do that, I want to enable flash attention you always want to enable flash attention. Attention is the most expensive part of the computation of the inference, both in terms of memory and the actual computation. And flash attention makes that faster and also makes it occupy way less memory. Otherwise, attention is going to be quadratic, and if you have a long context, it's gonna take way more memory than what you've got available. So then you put the size of your context. Let's say here I want 20,000 tokens. That's the size of my context. And then I put the model that I want, which I think in my case is in this models folder. Now, what this is going to do, it's going to load the tensors in the GPU. And then I'm going to say hello, and I can talk to the model. And if you go here, you are going to see in AMD GPU top that the memory of the GPU is utilized. And if we do write an essay on heap programming, heap being the ROCm programming language, obviously this is going to take a lot, and you can see the GPU being utilized for this. Now, by this utilization pattern, actually I can see a problem which I just realized. This is one of the two GPUs, and we have the second one, and as you can see, the model is also allocated to the second one, and it's using both GPUs. Now, llama-cpp does this by default, but we do not want llama-cpp right now in this particular setup to use two GPUs at the same time if the model fits in one GPU. So let me repeat that for clarity. If the model fits in one GPU, right now on llama-cpp, it is going to be faster to just run the model on that one GPU. If the model doesn't fit, then we can use both GPUs so that we can run a larger model. So in this particular case, what you would want to do, you would want to export these variables so that you only make one of the GPUs available, and this is going to work better and we're going to get better performances. I think we can't do it actually for this one because there is not enough memory for the context. Let me see if we can go like that. Oh, so maybe not for this model because it's too... All right, so it's simply not gonna want to load these into one of the GPUs. Okay, so this is gonna require more space. So let's take a model that should actually fit, which is probably Mistral. Oh, I know why it doesn't fit, because I got the incorrect model. I meant to use this one over here. I was wondering why, actually this one over here, I was wondering why that one wouldn't fit. Apologies. So again, I was just using a model that's way much larger. I want to use Quencoda, and I should be able to have my model loaded. This is now getting loaded, but this is going to go much faster. So if you go in here, one of the GPUs is not used at all, and the other one is, as you can see, used, but you will see the utilization is much higher. If I do this, you will now see that this GPU is utilized much more, and so that's what you get. Now, typically you don't want the CLI, so if you want to use a web UI, you simply change these to server, and this is going to listen on port 8080, and so you can just open these on port 8080. So there it is. And for example, I can say hello, and this responds to me. And then I can say write a heap kernel that multiplies to matrices. And so we can see these 100 tokens a second, and it's very, very fast. If you saw my other video on Strixelo, that's obviously much, much slower. So this is how we can use this. And if you want to use 2 GPUs, because the model is too big, as the model that we were trying to load before, which was the Qwen 3 Next 80 billion parameter model in Onslaught Dynamic Q4KXL quantization. That's a mouthful. Again, this will not fit into 1 GPU. It is just way, way too big, and it's going to fail, as we saw before. So because if you look at models and you look at that one, which is Qwen 3 Next, you can see that this is 43 gigabytes, so obviously it can't fit into one of the GPUs. Then we can say export visible devices 0 and 1. So now both GPUs are going to be available, and we can now load that model, and it's going to use both GPUs. And that just works. And again, typically you want to do llama-server. Llama-server also exposes not just the UI, but also a API if you want to program it. And now in here, we can reload this. And maybe I'm going to create a new chat. And you can see, obviously, this is it's still good, actually, 38 tokens per second, and it's now just going. You should also know that the Qwen 3 Next implementation in llama-cpp is really new, so it is not optimized yet. It will be much faster, probably, in the next few months, but even like this is an extremely capable model, and you get quite a decent performance. So this is us using both GPUs, and actually I will show you. Can you write the CUDA version? If you go here, you can see the utilization of 1 and of 2. Now, what you are going to notice, and this is why you shouldn't use llama-cpp with 2 GPUs unless you can't fit the model into one, is because llama-cpp splits the layers, so that you have a set of layers on one GPU and a set of layers on the other GPU. And I explained this actually in my RPC video, where I connected two Strixelo boxes. This works very similarly. It does model offloading. So what this means is that half of the model is on one GPU and the other half on the other one. So first the computation happens on the first GPU, then the output goes into the second GPU for the remainder of the computation. And while this is happening, one of the 2 GPUs is always idle, and you can actually see this pattern from one GPU to the other. Now, the final thing I want to show you is how to benchmark models. There is a tool called llama-bench, which most people use. And let's say I wanted to benchmark this model. That's how I would do it. I just change it to llama-bench. This sees the 2 devices, and it does the prompt processing benchmark and the token generation benchmark. And this allows us to see much better the utilization. But you see that because of this, we're not really fully utilizing the GPUs. And so we don't get the best possible performance. Mind you, this is still actually not terrible performance. But the other thing I want to show you, if you have a small model that fits into one GPU, let's say we have this Mistral model, this would, or actually decoder model that we saw before, that definitely fits into one GPU. If you use two GPUs, your performance is going to be lower than if you were only using one. And again, this is because of the way llama-cpp splits the layers of the model. It's an architectural constraint. So if now I did export heap visible devices 0, so I was just using one GPU, you will see that the performance is actually going to be better. As you can see here, this is 100 tokens faster for, especially for prompt processing, not too much for token generation. But if we increased the size of these tests, we would see a difference. Now, there is something else that you can do with llama-cpp with two GPUs. You can select the split, how it's going to split the model. So for example, you can say split mode, none, layer, or raw. By default, it uses layer. You can use rows. Now, in theory, from my understanding, this should be faster, but actually, in reality, at least on these models that I am trying, this is not faster. So if I say SM row, this is not going to be faster. It's actually going to be considerably slower for at least prompt processing, and I also think for token generation. So keep this in mind when choosing how to split the model. Again, that's just a no-go. None of the models I tried worked better with this. Okay, we saw how to run llama-cpp on this platform. We saw how to download models and how to use one or two GPUs. We also saw that there is a lot of work on AMD GPUs right now on llama-cpp. They've just pushed a patch specific for RDNA 4 and more is coming. So all of the performance that I showed in this video, that's very likely, not guaranteed, but very likely to improve in the next few months. Now, what I want to show you to close this is some of the benchmarks that I've done here, and you can see that I have different types of models with different architectures and different quantizations, and this is going to give you an idea when you want to choose which toolbox to use and which ROCm backend to use to get the absolute best performance. Now, if you see here, for example, what you want to keep in mind is that I am only using a dual GPU setup when a particular model like this one, the Q8KL for Quent3 Coda 30 billion, would not fit into one GPU, because as we saw, if the model fits into one GPU, it is right now, at least on AMD GPUs, at least in this setup, it's going to perform better on a single GPU. But again, these are the benchmarks, so take a look at them to figure out whether you think this is going to perform well for your use case. So that's the end of the video. I know that these videos can get very long, especially when I can't fully script them. It does take a lot of time to do the research. I haven't just gotten the cards built the server and installed the first version of llama-cpp that I found around. I built all of the different containers. I created a pipeline so that those can be updated and everybody can use the updated ones. And I ran a set of benchmarks across all of these different backends to show you right now what's the best performance with the best cards, and the amount of time that having all of these useful information in a video takes is a lot, and even just discussing all of these things takes a lot. But I really appreciate you sticking around until the end of the video. If you drop a comment below, that really helps the algorithm. Dropping a like, or if you are on mobile, that little hype feature that YouTube is trying, I would really appreciate it. It does help with as a signal that you want to see more. And indeed, if this video goes well and people are interested, in the comments below, I am definitely gonna make one with VLLM, and I have been working on toolboxes and improvements for VLLM specifically on this setup. I have very good results and I can't wait to share them with you in the next video.